Hello everyone, we're going to go ahead and do our exam 3 review. All right, so let's get started. For the very first question, we have what is your monthly take-home pay if you get a paycheck for $1,274.89 every 2 weeks? We're going to round our answer to the nearest cent, and we're going to assume there are 365 days in a year. So when we talked about how to calculate a monthly take-home pay or monthly payments that you have here, then what we need to do is we need to find the average monthly take-home pay. So since we know that there are different days in each month, February has 28, some months have 30, some have 31, we're kind of finding just the average, how much you would take in a month, not specifically like per the days in the month. And that's going to make quite a big difference when we do our calculations. So let's go ahead and go to our notes and work out this problem. So here's our question again. We're getting this paycheck every 2 weeks. So the best way that we can calculate our monthly take-home pay on an average type of basis is find out how much we make every day, calculate that for an entire year, and divide our year by the number of months in a year, which is 12. And that will give us our average monthly take-home pay, or just divvied up, however much we make in a year gets divvied up over 12 months. So let's go ahead and start. First place we want to start is taking our paycheck and dividing by the number of days that there are in every 2 weeks so that we can find how much we make in a day. So for this one, we call this daily take-home pay. So our daily take-home pay is going to be however much we make in our 2 weeks divided by the number of days in 2 weeks. So we make $1,274.89 every 2 weeks, which is 14 days. So we can calculate how much we make per day. Now, when we make these calculations, we will be making them in rounding to 2 decimal places because that's how much cents that we have. We have 2 decimal places for the smallest amount of money, which is pennies. So putting this into our calculators, finding the value, we should end up getting $91.06, and this is per day. This is our daily take-home pay. Now, what we want to do is take this number and assume for the year. So if I make this much per day in an entire year, which is 365 days, we were told to assume 365 days. So if we're assuming 365 days in here, then we can take the money that we make per day and multiply the number of days to find the yearly take-home pay. So yearly take-home pay, the amount we make each day, $91.06, times the number of days in a year, 365. So we use our calculators, we type in $91.06 times 365, and we should get that in every year we make $33,236.90, and this is a year. So this is the yearly take-home pay. So like we said before, when we find our monthly take-home pay, we're finding how much gets divvied up for each month over the course of the year. So to find our monthly take-home pay from our yearly take-home pay, we want to divide by 12. So our monthly take-home pay is we take our yearly $33,236.90, divide by 12 months. And using our calculator, we should end up getting $2,760 $69.74 a month. And that would be our monthly take-home pay. So when we're asked for our monthly take-home pay in a situation such as this, remember we're finding that average split over the 12 months over the year, not necessarily how much each day in that month is worth. Because each month could be different values or different numbers of days. So we can't guarantee so much for a 31-day month as a 30-day month. But we can guarantee it if we split it up over 12 months of the year after finding the yearly take-home pay. So, all right, that wraps up number one. Let's go ahead and go back to number two. So for number two, we have Jake got a short-term loan of $12,300 at an annual rate of 14% for 71 days. What's the amount of the loan at the end of the 71 days? So we have a situation here, we're having this short-term loan. And if we remember, short-term loans use simple interest. So we're going to calculate this value using simple interest. And we want to know what is the amount of the loan at the end of our time period. So we're looking for the amount, not necessarily just the simple interest that was gained. We're looking for the amount, which means our principal plus all of the interest that was gained. So we use our equation for the final amount at the end of our loan for this situation for simple interest. Then also, since it is a short-term loan, we do have a specific number of days, meaning that when we calculate our time, we'll have this ratio of our number of days out of the year. Because typically, when we use simple interest, we use time as years, but now we only have a certain number of days. So we're going to be using our ratios. So, all right, let's go ahead and go on over to our notes to work out problem number two. All right, so like we said before, this is with simple interest and the amount of our loan after a specific amount of time. So we want to remember that to find the amount of a loan after a specific amount of time with simple interest, our equation would be the amount of our loan is equal to the principal times 1 plus the rate times the time. So the amount is what we're looking for, and we can figure out each one of these values that we have. So our principal, we said, was however much the loan was originally for. So in our case, or for Jake's case, it's going to be $12,300. So the principal is $12,300. Then we have our rate of 14%. Remember, we always want that in decimal with our calculations. So our rate, 14%, is 0.14 in decimal. And then lastly, we have our time. Our time is 71 days. And we said it before, we're using a ratio because time is typically written in years. Since we have days, not years, we're taking that number of days and making it out of the days of the year, 365. So for T, our time, we really have 71 divided by 365. Whatever the number this is, this would correspond to the percentage of 71 days out of a full year. So this is how we'll set up our problem. So we can go ahead and fill in all of our values that we know. Our amount at the end of the 71 days should be equal to 12,300 times 1 plus our rate, 0.14, times our time, 71 divided by 365. So we can go ahead, and this is what we're going to plug into our calculators. So plug this in our calculators. Since this is money, we're rounding to 2 decimal places since we have cents is the smallest amount of money. So we go ahead, plug this in our calculators, and we should end up getting $12,634.96. So the amount of the loan after 71 days would be $12,634.96. So if we're thinking about interest, this question didn't ask us about the interest, but if we look at our answer here, we see it was really about a $300 increase, $334.96 to be specific. So our loan did not gain that much over the 71 days, although if you were to go the full year, this would definitely be a lot. So, all right, that wraps up number 2. Let's go ahead and go back over to our slides there to look at question number 3. Question number 3, we have Zach took out a loan for $5,800 and paid simple interest for 4.5 years. The total interest that he paid on that loan was $2,949.30. What was his annual interest rate? We're going to round that answer to 1 decimal place. So for this question, we're still working with simple interest here, but now instead of finding interest or the amount after a certain amount of time, now we're finding the rate, the value of R in our equation for interest. So we can go ahead and go on over to our notes to work out problem number 3. So for problem number 3, we're told how much the loan was originally for, meaning our principal. We're told how much time it was, 4.5 years, and we're told the amount of interest. So between those things that we already know, interest, principal, time, and we're solving for the rate, the equation we can use is the equation for simple interest. So the equation for simple interest is that the interest should be equal to the principal times the rate times the time. So we can go ahead and identify what we do have and then figure out what we don't, which is the rate. So we're told that the loan was originally $5,800, meaning the principal was $5,800. Then the time was 4.5 years. Time is always in years, so we don't necessarily have to specify that. Then we say that the interest was $2,949.30. So interest I was equal to $2,949.30. And we're trying to solve for R. So we're going to plug all of these things into our formula. So starting with our interest, we said our interest was $2,949.30, which is equal to our principal, $5,800, times our rate, which we don't know, times the time, which was 4.5. So in this case, we're trying to find R, and R is being multiplied by 5,800 and 4.5. So what we can do is we can go ahead and we can divide both of those values from either side to solve our equation for R. So we'll go ahead and divide both sides by 5,800 times 4.5. That will get rid of it on this side. When we develop our equation for R, our rate will be equal to $2,949.30 divided by 5,800 times 4.5. So we can go ahead and plug this value into our calculators. Now remember, we're going to go ahead and take this number and we need to turn it back into percentage for our final answer because the annual interest rate is given in percentage. So when we get this value, it's going to end up being 0.113 or about that value, which for us in percentage, we take that decimal place, move it 2 spots to the right, and our answer would become 11.3%. So when we say round to 1 decimal place, we're really talking about the percentage has 1 decimal place, not the actual decimal answer that we got. We want to convert into percentage and then make sure that we round to 1 decimal place from there, which technically means your decimal will have 3 decimal places. Then you turn it into percent. So, all right, that wraps up number 3. Let's go ahead and go over number 4. For number 4, we have Aldo borrowed money from the bank to buy a camper. He took out a personal amortized loan for $14,000 and at an interest rate of 5.6% with monthly payments for a term of 5 years. We want to know, what are all those monthly payments? What will the total amount be to repay the loan? And what will be the total amount of interest that he ends up paying? So for a problem like this, we have a specific amount of like payments that need to be made. We have the term, we have our rate, we have our principal. And so since we are making monthly payments, and that is the ultimate question here, for a problem like this, we want to use our equation for monthly payments, like based on our compound interest formulas. So these monthly payment equations mostly come from like paying off loans and things like that, including like student loans. So this came from our student loan section. So we're going to use that monthly formula or monthly payment formula to go ahead and calculate these values out. So let's go ahead and go over to our notes so we can do that. All right, so the equation that we use for this formula comes from our notes, but we have our monthly payments, which we call capital R. Sometimes it is referred to as M instead of R, but they mean the same thing. We're going to use R because that's what's in our lectures. So we have capital R is equal to P, the principal, times the rate divided by the number of times or the number of payments per year, which for us, since it's monthly, we will use 12. Then we divide by 1 minus 1 plus our rate divided by number of payments per year. And that will have the exponent of negative n times t. So negative the number of payments per year times per number of years. So this is our equation for our monthly payments. And that's where we're going to start with this problem. We start with monthly payments. Then once you know that, we'll know how much, we'll be able to calculate how much the total amount is. And then that will allow us to find the amount of interest. So with our monthly payments here, we can identify each one of these amounts. So we're saying the loan was 14,000. So our principal P was 14,000. Then we have the rate of 5.6%. So R would be equal to 0.056. Remember, always have to use decimal. And 5 years, so T will be 5. And the last value, N, is 12. Since since we have monthly payments, the N is 12. So you replace all the N's with 12 if you are using this for a monthly payment formula, and you don't really have to consider the value of N because it is monthly. But this is our generic kind of formula, but we can plug any periodic payments made into this situation. So, all right, we have this formula, so we can go ahead and plug everything in. So our monthly payments will be equal to 14,000 times 0.056 divided by 12, all divided by 1 minus 1 plus 0.056 divided by 12, all to the power of negative 12 times 5 in the exponent's place. So we're going to want to know what that equals. We need to plug this into our calculator. And so using a handheld calculator can end up being difficult because our handheld calculator probably doesn't quite set things up in this like nice and pretty type of way. So instead, we'll try to look at some tips and tricks on like using our handheld calculators for this. All right, so when we're in our calculators, we want to be very careful with our parentheses. And so when we set this up, we have a numerator and we have a denominator. So we want to make sure our numerator is its own set of parentheses. Then we want to make sure our denominator is in its own set of parentheses. So starting off with the numerator, we start with some parentheses. Then we had our principal, 14,000. And that's being multiplied by our rate divided by the number of payments per year. And because that is being divided, I'm going to keep that a little separate. We're going to put some we're going to put some parentheses around that. So we'll have 0.056 divided by 12. And that finishes off that portion. And that finishes off the numerator. So our numerator is put in now. So now we're going to do our denominator. Since it's a fraction, we're dividing. So we'll divide. Now we have some parentheses for our denominator. And our denominator starts with a 1 minus. And then we're going to have a new chunk in here. And that chunk is also going to have an exponent. So this whole chunk that I'm putting down here with this exponent, I'm going to give a parentheses for that. And then I want what's inside my parentheses that my exponent will go to. So I'll have another set. Now I can go ahead and do 1 plus, and now we have another ratio here. We have a fraction, 0.056 divided by 12. We want to make that its own value, so more parentheses, 0.056 divided by 12. So that's its own ratio. And then we have our 1 plus r over n here. Now we're going to go ahead and do our exponent. So our exponent, using the little caret symbol. And then we have negative 12 times 5. That finishes off our exponent. And that finishes off our entire denominator. We can go ahead and find this value, enter, and here is our answer. Once again, since we're working with money, we always round to 2 decimal places. So our monthly payments, or monthly payments should be $268.06. Since the number after 6 was a 2, it does not make 6 go up any higher. 6 will stay the same. So $268.06. So let's go ahead and write that down. So from our calculations, we have our answer, $268.06. And there are our monthly payments. So since we now know the monthly payment, we can go on to the next part, which is the total amount that pays the loan. So when we find amount to repay the loan, we're basically calculating how much money are we going to pay over this term of 5 years. We're paying $268.06 every month, and that's for 5 years. So we can find how much money in total that we're actually paying. So we take our monthly payment, $268.06, and then we're going to multiply that by the number of months in a year. So that value there would give us how much is in a year, but we want how much is in 5 years. So we multiply $268.06 by 12, and then multiply times 5, and that total should bring us to $16,083.30. So the amount to repay the loan is how much money we actually ended up paying at the end of whatever our term was. For us, that was 5 years. So we took our monthly payment multiplied by how much we would pay in a year, so by 12 months, and then how much we're paying in the entire term, however many years. So that's the amount to repay the loan. Now our last question here is, what's the total amount of interest he ends up paying? Our interest is going to come from our final payment minus our principal. That's how much interest we would have paid on top of our principal amount. So our interest is equal to the amount after a certain amount of time minus the principal. So for us, that would be $16,083.30 minus the original amount of $14,000. So the amount of interest that we actually paid would be $2,083.30. So that's how we calculate monthly payments and then finding out the total amount of the money that we're actually paying during that term and then how much the interest actually was. So, all right, that wraps up number 4. Let's go ahead and do number 5. For number 5, we say a bank offers an investment account with an annual interest rate of 1.48% compounded weekly. Hannah invests $3,300 into the account for 5 years. Assuming there are no withdrawals that are made, how much money is in Hannah's account after 5 years? How much interest is also earned on Hannah's investment after the 5 years? So we're answering 2 questions. We're saying how much money is in the account, so how much is there after a certain amount of time, and how much interest was that on top of the principal? So using all the information here, we have a certain amount of times is compounded, we have the rate, we have a principal, we have a time. So this will be our compound interest formula. Just finding the amount of time based on all of these aspects that we would gain over, in this case, 5 years. All right, let's go ahead and work this one out. All right, so like we said before, this problem here is going to use our compound interest formula. So our compound interest formula tells us that the amount in our account after T number of years would be equal to the principal times 1 plus the rate divided by the number of times you compound per year to the power of n, the number of times you compound per year, times T, the number of years. So this is our compound interest formula, and we can go ahead and pick out the parts of information that we'll use for our formula. So we know that the principal we said was 3,300. Then we have the rate was 1.48%. So that'd be 0.0148 in decimal. Then we have n, the number of times compounded per year. For us, we said it was weekly. We want to remember there's 52 weeks in a year. So this would be 52 for weekly. And lastly, T, we have the account is for 5 years. So T would be equal to 5. So we have all of our information. We can go ahead and plug all of this into our formula to find the amount after 5 years. So A of T is equal to our principal, $3,300, times 1 plus 0.0148, divided by n, which we said was 52. And then we have our exponent, which is n, 52, times however many years, which for us is 5. So the monthly interest or the monthly payment formula that we used earlier was difficult. This is also difficult, although not quite as complex, but we'll still go ahead and we'll show how to put this into our handheld graphing calculators. All right, so we have our calculator here. I'm going to go ahead and start plugging in our values. So we start with our principal, $3,300, and we're multiplying this by our by the rest of our formula here. We have 1 plus, and then we had r over n. R over n, we want to make sure that that gets calculated by itself. So we're going to put some extra parentheses. And we had 0.0148 divided by number of weeks in a year, 52. So that wraps up our r over n value. And we want to put parentheses around the 1 plus r over n. And then we have our exponent here. Our exponent needs to have parentheses as well. If we don't, it will take the very first number and the rest will be multiplied by our whole function, not as an exponent. So we have our exponent, 52 times 5. Press enter, and there we have it. We would have made $3,553, and it looks like 43 cents. It's 42. The next number is a 5. That 5 kicks the 42 up to a 43 cents. So $3,553.43. Not a whole lot much more after 5 years. But let's go ahead and put this into our notes to figure out how much interest was actually earned. All right, so we said that value that we got was $3,553.43. So that's how much money was in Hannah's account after 5 years. Now we want to find how much interest that was. We know that interest would be equal to our A of t value minus the principal. So our A of t value that we had was $3,553.43 minus our principal, which is $3,300. So subtracting those values, we should end up getting $253.43. So over 5 years, Hannah earned $253.43. Not really a whole lot. So, all right, that finishes up problem number 5. We'll go ahead and go on to our next one, problem number 6. Problem number 6, we have to plan for retirement. Amy deposits $1,603 quarterly in an annuity that pays 6% interest, compounded quarterly. Well, she's paying quarterly, so it makes sense. What's the total value of the annuity in 25 years? So this question here at the end, what is the total value of the annuity? This means that we are using the future value of the annuity formula. So we're going to use a different formula. It is a little bit different for annuities. So we want to take our formula from our notes to use in this situation. And we're going to use, of course, all of the information that we have in here with our formula. Let's go ahead over and work this out together. All right, so for number 6, we said that this would be the future value of the annuity. So that's the formula that we're going to use in order to find the value of the annuity in 25 years. So the future value of our annuity, we say is A is equal to R, our periodic payments, whatever they are. For us, that's quarterly, times 1 plus r, little r over n, so our rate divided by the number of times compounded per year, to the power of n times t minus 1. And all of that gets divided by little r over n. So this is our formula for the future value of our annuity. So we can go ahead as always and detail out what things we have and what we don't for our formula. So starting with that capital R, the monthly or periodic payments. So in our case, like we said, it's quarterly payments. So R is going to be $1,603 that gets paid quarterly. Then we can find little r, our interest rate, which we said was 6%. So in decimal, that'll be 0.06. Then we have the number of times it compounds per year, which we said quarterly. So n would be equal to 4. And then we have, lastly, we have t, which is going to be 25 years. So we want to know how much it is in 25 years. So we have all the values that we need, so we can go ahead and plug this into our formula. So we have A, the amount in our annuity after 25 years. It'll be equal to our periodic payments, our quarterly payments, 1,603 times 1 plus our interest rate, 0.06, divided by n, which is 4, to the power of 4 times 25, and all of that minus 1. And then all of that gets divided by 0.06 over 4. So this is our formula. Like every other time we've had a complex formula, we need to go ahead and be very careful when we plug this into our calculator. So let's go ahead and put it in our calculators so we can see how much our value of our annuity will be in 25 years. All right, so when we set this up, of course, we always want to separate our numerator from our denominator. So with parentheses, starting with our numerator, we'll take that very first value that we had there, which was our quarterly payment of $1,603. Now it's going to get multiplied by a whole lot of things. So we definitely need a set of parentheses. And the very first thing is going to have an exponent. So we need to make sure that that whole chunk stays together. So this will be my chunk with the exponent. And then I need to make sure that what gets inside the parentheses has the exponent. So one more. So we have 1 plus, and then I'm going to go ahead and I want to make sure my 0.06 divided by 4 gets calculated by itself. Another set of parentheses. So we have 0.06 divided by 4 wraps up that expression. Then we have 1 plus r over n has an exponent of, and now we have n times t, which you said was 4 times 25. So we had our exponent. Then we go ahead and we want to finish off our term with our exponent. Then we can subtract 1. And that finishes up our numerator. So that was our numerator. Luckily, our denominator is a little shorter. Our denominator is 0.06 divided by 4. So there's our denominator. So we can go ahead and see that this equals $366,771.28. The number after the 7 is an 8, which means the 7 gets kicked up to an 8 as well. So, all right, that's how we plug it into our calculator there. So let's go ahead and write down our answer. All right, so our answer here, $366,771.28. And there's our answer for the total value of our annuity in 25 years. So, all right, let's go ahead and go on over back to our slides, take a look at problem number 7. For number 7, we want to know how much would Joan have to invest to have $67,200 after 13 years at an interest rate of 3.74% compounded daily. So for a problem like this, we want to know how much does she have to invest, meaning how much should be invested originally to have this goal amount. So the amount after this 13 years should be $67,200. We have a time, 13 years, and we have a rate. So we want to know how much originally needs to be invested, meaning our principal. So for a question like this, compounded daily, so this is compound interest, we're going to find the principal amount. So the original amount for our equation. We use the same equation, but instead we're just going to solve for our principal. Let's go ahead and do that together. All right, so remember we're using compound interest. So our compound interest, A of t, would be equal to our principal times 1 plus r over n to the power of n times t. So this is our equation that we're going to use. Then we want to know all the amounts that we want. So we said that we want to have $67,200 after 13 years. So the amount after t years, A of t, should be $67,200. Then we have our time. We know that time will be 13 years. So t is 13. Then we have our rate, 3.74%. In decimal would be 0.0374. And lastly, n, or the number of times we compound per year. We said it was daily, 365 days in a year. So that's how many times we'll compound. So these are the values we're going to go ahead and plug into our equation. And we see that what's missing here is the principal. So let's go ahead and plug everything in. A of t, we said would be 67,200 equals our principal, which is what we want, times 1 plus our rate, 0.0374, divided by n, 365, all to the power of n, 365, times the number of years, which will be 13. So this is what we currently have. Now remember, we want to solve for the principal. And our principal is just being multiplied by the 1 plus 0.0374 divided by 365 to the power of 365 times 13. If it's being multiplied, that means that we can just divide it out. So we're going to go ahead and divide each side by the 1 plus 0.03, both sides by this value here. 74 over 365. So the power of 365 times 13. So it cancels out on this side, and then we're going to divide by the other side, meaning that our principal is going to be equal to 67,200 divided by 1 plus 0.0374 over 365, all to the power of 365 times 13. So let's go ahead and calculate this out in our calculator. All right, so when we plug this into our calculator, we have a numerator and a denominator. But if we notice, there's nothing going on in the numerator other than just a value. So we don't necessarily have to put parentheses around the numerator in this case. Since it's just one number, we're not multiplying or adding or subtracting or dividing or exponenting anything. So it's just 67,200. We're dividing that value by our denominator, which now we definitely need to have parentheses around. So we have some parentheses. This is the parentheses for our entire denominator. Then our denominator has an exponent, and there's something inside that exponent, so another set of parentheses. And inside this parentheses for our exponent, we have 1 plus, and now we have our rate over n, needs to be in another set of parentheses. We have 0.0374 divided by 365. Then we want to finish off that chunk there. Then we finish off what's inside our parentheses for our exponent. And our exponent, we said, will be 365 times 13. Finish off our exponent, finish off our denominator. So let's go ahead. And that's how much money would need to be invested in order to reach 67,213 years. $41,326.26. So let's go ahead and write that out in our notes. So from our calculators, $41,326.26. That's how much money would need to be invested in order to reach $67,200 after 13 years at an interest rate of 3.74% compounded daily. So, all right, we can use our formulas that were given to find the other things in our formulas, not necessarily exactly what it's designed to solve for. But, all right, that finishes up number 7. Let's go ahead and do our last problem, number 8. For number 8, we have Richie took out a student loan for $12,500 at an annual interest of 4% when he had 3 years left in school. According to the terms of the loan, Richie will need to make monthly payments for 5 years, and the loan accrues simple interest while he was in school. What's the monthly payment if the loan was subsidized? And what's the monthly payment if the loan was unsubsidized? So we want to remember one key thing about subsidized versus unsubsidized. A subsidized loan means that loan accrued interest while you were in school, but the government pays it off. Meaning that when you finish school, you are only responsible for paying off that principal amount and interest gained after completing school. And unsubsidized loans means that your loan accrued simple interest while you were in school. So then when you graduated, you owed more than you borrowed. Nobody paid it off for you. You gained interest while you were in school. That's the difference between subsidized and unsubsidized. So for finding the monthly payment, we're using the same formula for monthly payment. It's our principals that are going to be different between the two formulas. Everything is going to be the same except for the principal. The principal for subsidized will be the original principal of $12,500. But the principal for unsubsidized will be $12,500 plus the simple interest gained over the 3 years that Richie was still in school. So, all right, let's go ahead and do these problems together. All right, so the formula we're using is the monthly payment formula. So we can go ahead and write this out. Specifically for student loans, we say the monthly payment formula, we're going to use 12 for all of our ends in our kind of generic formula. So our monthly payment, this is monthly payment formula. We have R is equal to the principal times the interest rate divided by 12 divided by 1 minus 1 plus R over 12 to the power of negative 12t. So since it's very specifically monthly, we're replacing those ends with 12. That's what we do for student loans, since student loans are paid monthly. So, all right. This is the formula we're going to use for both subsidized and unsubsidized. The only thing that's changing is the principal. So let's go ahead and determine what everything else is. So in our equation, we need to know the rate, which is R. For us is 4%, meaning in decimal, it's 0.04. And then we have the time. So we have that graduated in 3 years, but the term of these payments is 5 years. So we're multiplying by 5. So T is 5. The other things that we need are the principals. So for our subsidized, we'll start with subsidized. For a subsidized loan, principal is going to be our original principal. Our original principal being $12,500. So for our subsidized, we use our monthly payment formula with our original principal, $12,500. So we have R is equal to 12,500 times 0.04 divided by 12 divided by 1 minus 1 plus 0.04 over 12 to the power of negative 12 times 5. Now remember, this is money, so we're rounding to 2 decimal places. And this is a more difficult formula here, so we're going to use our calculators together. All right, so we're going to go ahead, plug in everything. But of course, starting with our numerator, we have our principal, 12,500, times our R over N portion, which does need to be separate. So some extra parentheses there. So we have our numerator divided by what's in our denominator, starting with our 1 minus, and then we have our whole big chunk in there with the exponent. So we're going to have our exponent in there, but we also need to have what's inside the exponent. So we have 1 plus our 0.04 divided by 12, which needs to be calculated itself, so parentheses. Then we have our term, which has our exponent of negative 12 times 5. That wraps up our equation, so we can find our answer, which should be $230.21. $230, and it says 20, but the number after the 0 is a 6, making the 0 a 1, giving us $230.21. So that would be the monthly payment if Richie took a subsidized loan in this situation. So let's go ahead and write that down and then work on unsubsidized. So from our calculations for subsidized, we had $230.21. All right, now we want to do unsubsidized. So unsubsidized, we said that our principal will gain interest while Richie was in school. So our principal is going to be the amount after 3 years gaining that interest. So our principal for this case, we can use the formula for simple interest, or the amount of simple interest after a period of time. So this amount would be equal to our original 12,500 times 1 plus our rate of 0.04 or 4% times the number of years that he was still in school, which we said was 3 years. It took Richie 3 years to graduate from school. So this interest gained for 3 years. So there is our formula. So to find this amount, our new principal in this case is using this formula. And we should get that our new principal is actually going to end up being $14,000. So between those times that you had, you would end up gaining this amount. So instead of paying off $12,500, which is what Richie actually borrowed, he's now paying off $14,000. So everything is going to remain the same for our formula. We're just using $14,000 for our principal instead of $12,500. So our monthly payment formula for unsubsidized would end up being 14,000 times 0.04 over 12, all divided by 1 minus 1 plus 0.04 over 12, all to the power of negative 12 times 5. And just as before, we're going to go ahead and go to our calculator to calculate this out together. All right, so our new formula here, just using 14,000 instead of 12,500 in our formula. Everything else is going to be the same. We still have our rate divided by number of payments per year, so we have 12. Then we have our denominator here. We have 1 minus 1 plus 0.04 divided by 12 to the power of negative 12 times 5. So there we have our formula there. And our monthly payment for an unsubsidized loan would end up being $257.83 a month. So it's not that huge of a difference between subsidized and unsubsidized per month, but over the 5 years, that would end up being a good amount of money that you're ending up paying extra just from the different type of loan that you actually ended up borrowing. So, all right, let's go ahead and write our answers together in our notes to finish off our last problem, number 8. All right, we said our answer there was $257.83. So roughly $27.83 more than if it was subsidized. So that is the main difference between subsidized versus unsubsidized. It's the same formula, it's the same setup. The only thing that's changing there is the principle. So, all right, that wraps up the end of our exam 2 review. So, good luck studying. Good luck on your exam number 2. I'll see you in the next one.